Have our balanced chemical equations, we need to know what to do with them. And so that's when we jump into this new concept, the mole. So we're going to start doing some stoichiometric problems. Stoichiometry is just dealing with relationships quantitatively between reactants and products. So essentially, if I know how much of any given reactant or product that I have, I can relate that amount to anything else. So if I have a certain amount of reactants, I can find out how much of a product I can make, right? So it's really useful when you're in the lab and you want to know how much of a certain product you can make. So we need to know how to do these kinds of calculations. And they're actually relatively simple, right? You have to understand how to do them first, but it's always pretty straightforward. You do the same process every time. So if you look at this example reaction here, this synthesis of aspirin, right? The first basic concept of this is to realize that if I have an equation like this that is balanced with all ones, essentially I have one of each of those molecules, right, that's going to take part in this reaction. So if I have one of those salicylic acid molecules and one acetic anhydride molecule, I can make one aspirin molecule, and then I'll also have that acetic acid product. So when I'm looking at this, I'm thinking about it as literally one molecule. But the problem is that's not even reasonable. Molecules are so tiny that there's no way you could just be dealing with one molecule of each thing. You obviously have way more than one molecule of each of those things if you have a substance that you can even measure in grams. So we don't really use that idea anymore. That's where this mole concept comes into play. A mole is 6.022 times 10 to the 23rd of anything. So if I have 6.022 times 10 to the 23rd salicylic acid molecules, that's exactly 1 mole of that substance. And it seems like an arbitrary number, but what it does is it makes the math easy for us in the long run. So we're going to talk about an atomic mass, which is that mass of an atom in AMU, but then we're also going to talk about a molar mass, which is a completely different thing, but also related. So the atomic mass for any given element is found on the periodic table, right? I know that one carbon atom from my periodic table has an average atomic mass of 12.01 AMU. But remember, if you remember us talking about that mass unit, that AMU, we know that we made up that unit because it's so tiny we can't even measure it, right? If I wanted to express that in grams, it'd be a ridiculously small number. So I need to relate that to a large amount of carbon atoms and be able to still have that be useful. So actually we're going to jump to this calculation over here. The whole purpose of Avogadro's number is that it can take a really, really small number. As you can see, this number of grams in 1 AMU, right? Excuse me. The conversion factor here, this number of grams that's equivalent to 1 AMU, is really, really, really small, right? But also, the number of atoms in 1 mole of a substance is really, really, really big. So what essentially we're trying to do is get those things to cancel out. So when we do a calculation here, right, and I multiply and divide just like anything else that we talked about in the past, if I take that 12.01 and I multiply it by 6.022 and then I multiply that by 1.661, it turns out I get a number that looks a little bit like this, right? So if you're using your calculator, you can see the same thing. But 12 times 6 times 1 is going to give me a number of about 120.1 on your calculator times 10 raised to the negative first power. Now remember, I just used my rules for that 10 to the power, right? And since I'm multiplying, I'm going to add, and 23 plus a negative 24 gives me a negative 1. But I also don't like that number right now because A, it's not in scientific notation, and B, this number is reasonable enough that I don't need scientific notation for it. Right? What I would actually do to adjust this is just take it out of scientific notation. If I added 1 to that exponent, that means I have to move the decimal to the left one time, and it turns into 12.01, right? Which, surprisingly enough, is the number I had to begin with, right? The whole purpose of that 6.022 times 10 to the 23rd atoms is literally to make that 1.661 times 10 to the negative 24th go away, right? So what that effectively does for us at the end of the day is it changes AMU into grams, and it changes atoms into moles. So I have this new unit, grams per mole, but I have the same number as I had to begin with. So I can think about one carbon atom as having a mass of 12.01 AMU, or now I can think of 1 mole of carbon atoms having a mass of 12.01 grams. I have the same number, just a different unit, right? So at the end of the day, the whole purpose of Avogadro's number was to make it so that that would be true. 12.01 AMU is the same as 12.01 grams. So it doesn't really matter what context you're using, that number off your periodic table is still going to work. So I have atomic mass that we talked about before, right? It's an average of all those different isotopes of carbon, and it's actually an AMU. But now I have this new concept of molar mass that's in grams.